The particles of matter with which we are familiar have properties like spin, an intrinsic spin. They are like spinning tops. These are the fundamental particles. They also have various types of charges. Electric charge is very familiar. Less familiar are things like isotopic charge, which distinguishes between a proton and a neutron. And these things are usually ascribed, for want of a better name really, to what we call internal symmetries. These are the intrinsic properties of matter which distinguish one particle of matter from another and also determine the type of dynamics in which this particle participates. So we are faced with the problem of trying to understand the deep nature of spin and also the deep nature of these so-called internal symmetries, electric charge being the most commonly understood example. Now, so far as intrinsic spin is concerned, angular momentum is connected with rotation, and rotation is something which is connected with space and time. You can see a rotating body, and you understand by that rotation something which is happening to the physical magnitude of the body in space which we inhabit. The question is charge, or the so-called internal symmetries, do they have certain rotations of a similar sort associated with them? Nobody knows. In this endeavor, we had to, there was a theory which was first propounded by Cartan in 1922, which was a generalization of Einstein's gravity theory. Einstein had considered gravity to arise out of concentrations of matter, just as Newton had, but of course Einstein did it in a far different geometric framework. He conceived of density of matter or energy as producing a curvature of space and time. Cartan had the idea that spin could also give rise to gravity by producing a torsion in space and time. And it's the aspect of torsion of space and time which we have found to generalize very naturally and very easily to comprehend internal symmetries as well. They seem to form a one whole, a unit, which is of extraordinary coherence. And at the moment, we are trying to see if the idea goes deeper and whether, just as Einstein was able to use the curvature of space and time to give to his gravity theory a depth which was not present, say, in Newton's gravitational theory. Likewise, by using the Cartan ideas of torsion, which Cartan had used for ordinary spin, for rotation, whether we could, taking those ideas and looking at the extension which we have made of those ideas to include internal symmetries, get down to something much deeper. This is a continuing effort. We have completed, as I said, the first part, and we can see the synthesis. Whether it has a deep significance, we do not know yet.
How is this related to a unified field approach? You haven't yet talked. You've talked about torsion, but you haven't yet talked about the quantum principle. How do the two relate?
Well, all our theory is couched within the quantum framework. So in that sense, we are buying quantum theory right from the beginning. When you speak of the unified field, of course what we are saying is that just as presently one of the ideas which is now very current in our subject is that the weak interactions and the electromagnetic interactions both are described by the same field. What we have done is to show that spin 2 mesons, which are responsible for part of the nuclear force, and the gravitational interaction, which is also mediated by gravitons of spin 2, have the same. And so in that sense, we have achieved a sort of unification, if I may call it that, which would be very strange to Einstein if he was alive. We have used he was wanting always to extend his theory to include electromagnetism. He failed. We have used his theory to describe nuclear forces. So, you see, he did not live to see the existence of spin 2 particles among the nuclear particles. That is, particles which are just relatives of the graviton, if you like. They interact with greater strength. So from our point of view, we in fact call these particles, they are the F meson, technically known, we call them strong gravity. And we say that nuclear physics is strong gravity. So in that sense, we do claim to have a certain unification.